Hi everyone. Finally, we're ready for the Riemann-Lebesgue theorem. And in this video, I'm going to show the first implication of the Riemann-Lebesgue theorem. Before we do that, I've just got a few more lemmas. They're very small. We'll go through them very quickly, and then we'll get into the main theorem here. So, lemma 1, all it says... Oh, sorry, I forgot to put proof here. Lemma 1 is just that the measure of a singleton is 0. This is a relatively standard exercise. If I go through lemmas 1 or 2 too fast, pause the video, review your definitions. They're good exercises. Try to do them yourself. They're not too difficult as far as measure theory proofs, I guess. But they're standard results that you should really try to work through and keep in mind, because they're standard tools that you use over and over and over again. So all you do here is you take a singleton. Well, what's a set slightly bigger than it that it's inside of? Well, it's just a small interval here that contains the point x. That measure is epsilon, just from the definition of Lebesgue measure. And then that holds for all epsilon greater than 0. So take epsilon to 0, and you get that that measure is 0. The second one is that the countable union of measure 0 sets has measure 0. So I have a countable collection AN. Each one has measure 0. And I'm considering this set, which is the union of all of them. Then that set also has measure 0. To prove this, you simply use subadditivity, which is a property we proved a few videos ago. So go back and rewatch that if you're not familiar with it. So subadditivity says if I take a union, any union, doesn't have to be disjoint. If it's disjoint, this is exact equality. If it's not disjoint, then in general, it's less than or equal to. That sum is 0 because each one is individually 0, and you're done. So again, review your definitions. If you're new to measure theory, that's a bit fast, then review the stuff. Make sure you understand those proofs. The next one is sort of a analysis 1 type of exercise, but it's key to the Riemann-Lebesgue theorem. It's a small lemma. It's just a different characterization of discontinuity. Okay, so all it says is f is continuous at x if and only if its oscillation is 0. This is really why we introduced oscillation, because oscillation is what we're interested in. We want that characterization for the proof. It's just cleaner. So I'm just going to prove one implication here. You can pretty much just undo the same logic the other way. So I'm going to assume f is continuous. Let epsilon be greater than 0. Let delta be such that for all y, such that, just x minus y is less than delta implies f of x minus f of y is less than epsilon over 2. That will tell me that the oscillation of f at x okay, let's not do it that way. So this tells me that the supremum of y in x minus delta to x plus delta, f of x minus f of y, is less than or equal to epsilon over 2. And that tells me that the oscillation of f of x is indeed 0. If you give me an epsilon, I can always exhibit to you a small interval containing x where the supremum is less than or equal to epsilon. So the oscillation is 0 because it is the limit as delta goes to 0 of this expression. And as delta goes to 0, that epsilon goes to 0. So, and then, yeah, like I said, I'll just prove that one direction. That way we can get into the main part here. So that's just a characterization of continuity that we want. So Riemann-Lebesgue theorem, part 1. So again, as always, we're taking a bounded function. Bounded function on a closed interval. Be bounded and Riemann integrable. And I'm going to define the set of discontinuities of f to be the set of all x and I such that the oscillation of f of x is strictly greater than 0. And again, so this is the main part here. So I just wanted to give you a flavor of why this is true. But we want this alternate characterization. So if I flip that to greater than 0, that becomes f is discontinuous at x if and only if its oscillation is strictly greater than 0. And so then the conclusion is then the measure, the set of discontinuities is 0. So basically, the set of discontinuities is super small. It's like saying that pretty much at every point, there can be exceptions, but pretty much every point, f is continuous at that point for Riemann integrability. Well, if Riemann integrability holds, that tells you about the discontinuity. Part 2 is actually proving the other way. It's an if and only if statement. So I'm going to set epsilon greater than 0, and I'm going to show that the measure of df is, well, sort of. Indirectly, I'll show that, but you could show it that way. I'll do it slightly differently. But basically, measure of discontinuity of f is less than epsilon for all epsilon is essentially the outline. So, but I'll do it slightly differently on a slightly different set, and then I'll take a union of those sets. So let k be in the natural numbers, so that we're going to fix that for now. And now I'm going to invoke Riemann integrability right off the bat to name a partition such that the upper Darboux sum minus the lower Darboux sum is less than epsilon over k. The over k is important here. So the upper sum minus the lower sum is the set oscillation of f. I didn't leave enough space here. Okay. So this is times delta. I'll just put it delta xn. That's really xn minus 1. So that is what the upper minus lower sum is. And now I'm going to define B to be the set of all n between 1 and n such that the open interval xn minus 1 to xn intersected. Oh, I didn't define it. Let's cut this. I just move it. Okay, yeah. Sorry, I forgot to define another set. So I'm going to define AK to be the set of all x in the interval such that the oscillation of f at x is greater than or equal to 1 over k. And just note, that is a subset, set of discontinuities. It's basically saying it's discontinuous with a jump at least of size 1 over k. So as we take k to 0, our jumps get smaller and smaller, but we're still discontinuous. And that's the main theme behind the proof. So this intersection is non-empty. that means we have a discontinuity on that subinterval. So this is a set of indices here. So we note that for n in B, the supremum over x of the oscillation of f of x is greater than or equal to 1 over k. Now, the set oscillation of f, okay, so then I'll put for n and b, the set oscillation of this set is greater than or equal to the supremum over x of the oscillation of f at x, because x is chosen on the interior. So notice we did not address this point and this point. Supremum over x in xn minus 1 to xn, x in. Because the oscillation, so basically the reason for that is because I want to confine my attention to the subinterval, but I can't really consider the endpoints here because the set oscillation has to take, or the oscillation has to take a open interval containing the point. And so on this side, if I go a little bit to the right, I'm jumping into the next part of the partition. This guy, if I move a little bit over to the left with an open interval, I move into the other side of the partition. So that's why we're restricting this to an open set here. So this is greater than or equal to 1 over k. That tells us, okay, that the sum over n and b of 1 over k times the sum xn minus 1 is less than or equal to the sum of the set oscillation f xn minus 1 to xn xn minus 1 is less than epsilon over k. The k's cancel, and so now I'm left with the sum. So the reason why I want that k is because now this looks like the measure of an interval. That's less than epsilon. That's kind of nice because now we're saying the width of the measure. So these are also another nice thing about the open intervals is we don't have to worry about overlap. So this is exactly equal to that union. They're disjoint. Remember, that's just a property of unions. Okay, so we got one more step here, small step. So remember, we did not consider discontinuities at the at the interfaces of the subintervals. So AK is actually contained in the partition unioned with this set. So notice there could just be one discontinuity in each of these subintervals, but if I consider the whole subinterval as having a discontinuity of order 1 over k, that could happen. So this is a pessimistic bound, really. But there could just be a single point or no point, or just a single point here in this set because B is the set where the intersection is non-empty. The P, we have to throw P in. So P, remember, this is equal to the endpoints of our mesh. So that's an equality. Okay, so that now tells us that the measure of AK is less than or equal to the measure that set plus, well, let's just go straight less than. So we're splitting these. They're disjoint because these are open intervals. And that's less than epsilon. Okay? Then this is equal to the sum. I'll go to a different page here because I'm not sure if you guys can see that still. So just to rewrite that, that's measure of AK is less than the measure of this plus epsilon. That is the sum n equals 0 to n of the measure of x n, because they're disjoint, they're singletons. Okay, and this is why we prove this. This is n times 0. They're all measure 0 sets because they're all singletons. Okay, and then remember 0 is less than or equal to this. Okay. For all epsilon greater than 0. So that tells us that the measure of AK is 0. And remember that AK is this set. Such that the oscillation of f of x is greater than or equal to 1 over k. Now we're going to use lemma 2. So now we've used lemma 1 and lemma 3 at this point. Now we're ready to use lemma 2. So we're almost there. If I tell you I want to jump bigger than 1 over k, I'm going to allow only those ones. I've got that taken care of. It's a measure 0 set. But notice that df is a set of all x and I such that the oscillation of f of x is strictly greater than 0. That is also equal to the union over k in the natural numbers of the set of all x and I such that the oscillation of f at x is greater than or equal to 1 over k, because 1 over k goes to 0 as k goes to infinity. So you really could do something different here. It doesn't have to be 1 over k. It could be 1 over k squared. It could be anything as long as that expression goes to 0 and it's a countable union here. So this is precisely the AKs. But we just proved that for all k was arbitrary, remember? So we didn't have any assumptions on k. K was arbitrary, so the measure of AK is 0. By lemma 2, the measure of the set of discontinuities is also 0. And we are done with that direction.